Now in this part I will discuss the half-life of second order reaction. Now upon integration of the differential form of the rate equation, we obtained that the integrated rate equation is like this. So 1 by C equal to Kt plus 1 by C0. This is the rate constant and this is the concentration at time t, concentration of the reactant remaining at time t, and this is the initial concentration of the reactant. Now half-life is defined to be the time required for 50% completion of the reaction. So as per definition it will be when T equal to T half, the remaining concentration will be 50% of the initial concentration, that is C will be C0 by 2. Now you put here, so it will be 1 by C0 by 2 when we have T half here plus 1 by C0. So it is 2 by C0. Now we take this to the right hand side. So we have 2 by C0 minus 1 by C0. So Kt half equals to 1 by C0. We take this to the right hand side. So that will give us 2 by C0 minus 1 by C0, that is 1 by C0. So the half-life for a second order reaction is inversely proportional to the initial concentration. So if we start with 2 molar concentration of the reactant for any second order reaction, and if we find that the half-life for that reaction is 20 minutes, this is for example 20 minutes, then after 20 minutes we will have 1.0 molar of reactants to remain left. Now after 20 minutes 1.0 molar will left from 2.0 molar. Now what will happen when we allow another half-life? So after another half-life it will be 0.5 molar. Now we have noticed in the half-life of first order reaction that this half-life remains same. That is, in the second case also the half-life will be 20 minutes independent of the initial concentration. But in this case, in the second order reaction, the half-life is a function of initial concentration and it is inversely proportional. So when the concentration gets half, it will be doubled. So for the next half-life it will require 40 minutes. Now what will be the time required to get it another half? So it will be 80 minutes. So this is the half-life of second order reaction. Now see, as the reaction is approaching, the concentration of the reactant will fall. So with the passage of time, the concentration of the reactant will fall gradually, and you see that if the time for the fall of concentration from 2 molar to 1 molar is 20 minutes, then the fall from 1.0 molar to 0.5 molar is 40 minutes. So with decrease in the concentration, the time required for 50% completion increases. So less the concentration, more will be the time required to complete the reaction. So as the reaction proceeds, concentration falls, but the half-life increases. So with time, we see the time required for 50% completion will increase, and when say it is about near the completion, so it is very small amount left, say 0.0000, a very small amount left, say it is 1, then you will have a very large T half, very large, since it is inversely proportional. So when the concentration left is very large, very small, that is reaction is almost to the end, then the T half is very large. So at the end of the reaction, the time required for 50% completion will increase rapidly. So we can say that it will never come to an end. Since at the limit of tends to 0, it will require tends to infinity to 50% complete only. So what we can say is that this reaction will never complete. Now if you remember the half-life of first order reaction, this I am drawing for the first order. You see, when we plot C versus time, we get here this one. So this graph meets the time axis asymptotically. That is, it will touch this axis at infinite time. What does it mean? That this concentration will be 0 when time is infinite. Or in other words, what does it imply? That this reaction will never come to an end. Also in part 8, I have explained to you that in the relation C equal to C0 into e to the power minus kt, this graph is according to this equation. When we put t equal to infinity, we get C equal to 0. So at time infinity only, the concentration of the reactant will come to 0. So the reaction will end at infinite time, or in other words, the reaction will never come to an end. So first order reaction never completes, and likewise second order reaction also never completes. And for first order, we have the half-life to be independent of initial concentration, but here in case of second order reaction, we get the half-life to be dependent on the initial concentration, and it is inversely proportional. So we can conclude that a second order reaction like first order will never complete. Now at this point, anyone may have a query that in part 1 I have started with the introduction, where I have said that we will deal with the reactions having moderate rate, so that they complete within 2 or 3 periods, so that we can perform experiment in our chemistry laboratory. Now here I am giving you a statement that a second order like first order, so a first order reaction and the second order reaction never completes. Never completes. So isn't the two statement contradictory? In part 1, I have told you that we will deal with reactions having moderate rates, and in part 12 I am telling you that a second order reaction and first order reaction will never complete. So is it the conclusion that we will deal with only those reactions which have moderate rates and which are not first order and second order? No. We will deal with first order and second order reaction with moderate rates and also zero order reaction in laboratory, because this is theoretical. Reaction actually completes, but you have to understand it, understand the mechanism behind it. When a reaction proceeds, say Na arrow product, the rate equation is minus ddt of C equal to K into C to the power N. So it is an nth order reaction. Now as the reaction proceeds, product is formed. So between reactant you have a lot of product which will interfere the understanding of the reactant molecules. Now if it is a first order, then there is an understanding such that if you start with 2 molar concentration, the time required for getting it to be 1 molar is equal to that to be converted to 0.5 molar. So if it is 30 minutes T half, it is also 30 minutes. So it is a result of our understanding for a first order reaction. Now for a second order reaction, it is, if it is T half equal to 30 minutes, then for the second case it will be 60 minutes. This is also a result of understanding. Now this understanding will get disturbed when lot of products will be formed and it will interfere the understanding. So it is generally considered that there is a relaxation time for any reaction, and after that relaxation time you must not take any data from your experiment, since that will give you erroneous result. And for this you will notice that while we perform an experiment in laboratory, we actually deals with the initial rate. So we just start the reaction and we take the data up to 15 minutes or 20 minutes and not more than that. Since after the relaxation time of the reaction, the understanding that is prevailing within the reactant molecules will get disturbed by the formation of a lot of product. The reaction will, however, actually come to an end, but will not maintain the order with which it has started with, since the product will interfere the understanding. So while taking the data, you have to take it within 15 minutes or 20 minutes from the start of the reaction, and you must not wait for a long time. The reaction, I am repeating, the reaction will come to an end, but if we start with a second order reaction, the reaction will not come to an end, and it will not maintain its entire journey through second order reaction. It may approach with any other order or second order or first order or zero order, since the understanding gets destroyed. So we will take the data. Theoretically it says that it will never complete, since we have not given any input of the disturbance of understanding by the product within the equation. So this is giving us the true picture that it will never complete. But in reality, there is a disturbance of this rate equation, and the disturbance is not given input in this equation. So in reality we will have that reaction will complete, but in theory we get that it will never complete. Do you understand what I am telling? In theory it will never complete, but in experiment it will complete, since the product disturbs the understanding and the reaction approaches after a certain time, that is after relaxation time, through some another mechanism, through some other order. So that must not be dealt in the experimental data for a reaction having a particular order. Now I will discuss zero order reaction in the next part. Please study all the parts thoroughly and practice it, otherwise you will be unable to remember.